Let us look at the exact differential. Now, here, if you designate the integral as I, and you're integrating along a curve, the exact differential is the partial derivative of z with respect to x. Here, z is a function of x and y, alright? Partial derivative of z with respect to x dx. So you integrate this with respect to x plus partial derivative of z with respect to y, and just integrated with respect to y dy. Alright? Now, this delta z by delta x is the integral in the direction of x. The component of the integral in the x direction, and this of course is a component of the integral in the y direction. Alright? Now, if you should find delta by delta y, you differentiate delta z by delta x with respect to y. What you're going to get is delta square z by delta y delta x. You see that? And now, suppose you find the derivative of this with respect to x. You find delta z, or the partial derivative with respect to x of delta z by delta y. What you would get is delta square z by delta x delta y. Now let's put these together. You have delta square z by delta y delta x, and delta square z by delta x delta y. But guess what? You remember that in a previous lesson we learned that this, as it is, will always be equal to this. So in that case, they would be equal. Alright? Always equal. So, one way to test if an integral is an exact differential, where you have a line integral along a curve, if it's in the form p dx plus q dy, what you do is find the derivative of p with respect to y and see if it is equal to the derivative of q with respect to x. In this case, p would be similar to delta z by delta x, right? And this would be q. Q would be similar to delta z by delta y. Let us see an example of that. And by the way, before we do that, remember, when you have a situation like this, right? No. You have this derivative p dx q dy. Alright? What you're doing, you're integrating p, or you're integrating delta z by delta x with respect to x, and delta z by delta y with respect to y. Now, if you break this up into two parts, you're looking at the integral along the curve of delta z by delta x dx plus the integral along the curve of delta z by delta y dy. Alright? So that's what's going on there. Now, if you integrate this, you will get z. If you integrate this, you also get z. If you integrate delta z by delta y dy, you get z, right? Because remember now that if you consider cancelling the dz with the delta z, the dx with the delta x, you're integrating 1 delta z, which will give you z. And if you consider that you cancel the dy with the delta y, you're integrating delta z. You're integrating 1 delta z, which will give you z. Alright? But let's look at this example. You need to evaluate the integral, the line integral along the curve C of 3x squared y squared dx plus 2x cubed y dy. Alright, so let's see something here. When you consider this, right, let's see if this thing is an exact differential. If you find the derivative of 3x squared y squared, you find the derivative of this with respect to y, right? Remember, this is what you're finding derivative with respect to y. What you're going to get is 3 times 2 is 6, using the power rule 6, x squared y. See that? So this derivative with respect to y gives us 6x squared y. Now, what is the derivative of this with respect to x? The partial derivative of this with respect to x of 2x cubed y is equal to, alright, let me put it down here, running out of space. This is equal to 326 x squared y. So you see, it's the same thing. So we can see it is an exact differential, right? The other thing we can do, as I showed you before, suppose we integrate this with respect to x. The integral of 3x squared y squared dx would be equal to what? Well, this would be 3x cubed over 3 y squared, which will be 3 cancels 3, so it's x cubed y squared. Alright, suppose we look at this one now and say, what is the integral of 2x cubed y with respect to y? What we're going to get is 2x cubed y squared over 2. So what we have, 2 cancels 2, so you get x cubed y squared. So x cubed y squared here, x cubed y squared here. Alright? So the function that we have here, z, is x cubed y squared. But anyway, what this shows is that the integral we have here is an exact. That is called an, well, I should put the thing there, not the brackets around it, because both of them will be integrated. But the integral we have here is what you call an exact differential, right? Now, the thing about an exact differential is that it doesn't matter where you start, right? And where you go to. Because, well, what I mean by that, if you start here and come here, it doesn't matter if you go this direction or straight along here or this direction, right? It doesn't matter the path that you take, it will give you the same result. In our next video, we'll look at the same example and see an integral along a curve taking different paths and seeing if it will produce the same result. So I'll see you then.